now we're recording. So welcome to the Accessibility in Math and STEM webinar. I'm really excited this week to have a moderator, Eva Ozanne from Olympic College, who's math faculty and a member of their accessibility work group. And then we have a few panel presenters that will be kind of going over some of the unique challenges and solutions when it comes to accessibility in math and science. So Eva, I'm going to go ahead and hand it over to you.
Great, thank you, Jess. I am really excited to be a part of this today. I know whenever I go to a workshop or a webinar, I always feel like, what about STEM? So I'm excited that we get the chance to talk to everyone today and get some of those questions answered. So we are going to start with Ms. Krista Greer, and you're going to give us an overview of accessibility challenges that are unique to math and STEM. So go ahead and take it away, Krista.
Great. I'm going to share my screen here. Okay. All right. Are we good, everyone?
Yeah, looks great on this end.
Perfect. So my job is to give everybody a brief explanation and framework as to what accessibility is, what do we mean when we talk about STEM accessibility, and specifically talking about LaTeX versus MathML. So I will share that my perspective is that I have been working in disability services for the last decade, and I have specifically been focusing on document remediation. So my job is to help students with disabilities who specifically have areas of perhaps challenges regarding documents that are not constructed in a way that is usable for them. And so I would take documents received from instructors, and my fabulous team and I would remediate them or change them so that they could be useful for our students that we were specifically working with. Let me introduce to you the definition of accessible that I typically work from. And I will read this. This is directly from the University of Montana, the Office of Civil Rights Settlement back in 2012. And I'm going to emphasize a couple of key words. So accessible means that individuals with disabilities are able to independently acquire the same information, engage in the same interactions, and enjoy the same services within the same time frame as individuals without disabilities with substantially equivalent ease of use. So when you boil all this down, people with disabilities need to be able to do all the things that everybody else can do. They need to do it independently in the same time frame and have access to the same experiences. So who needs accessible STEM? STEM being science, technology, engineering, and math. At the very least, it needs to be accessible for those that have learning disabilities, perhaps traumatic brain injuries, those who are blind, perhaps low vision, perhaps some mobile limitations, but also consider situational experiences. So for example, let's say that you're a student, doesn't matter if you have a disability or not, but you're in the library or in the gym or you're commuting, and maybe you need to have access to an audio version of your STEM content. Maybe you have crying or sleeping children that you are trying to work around. Maybe there's something in your environment that is going to challenge the way that you normally access your materials. So let's say you have sleeping children, the lights are really dark, and having the light from your tablet to read your math book is really going to be disruptive. Why couldn't you listen to your math content? Like, why can't that be an option? So that's the framework for, at the very least, kind of who needs accessible STEM. And now let's talk about some keywords that most of us have probably heard at least one of them. So the first word is called LaTeX. So LaTeX or LaTeX, depending upon which part of the country you're from, it's a document preparation system for typesetting. And it includes features designed for the production of technical and scientific content. LaTeX is the de facto standard for publication of scientific documents. So I would surmise that most instructors who are in STEM fields know what LaTeX is and either know how to make it or they know how to convert into LaTeX. Excuse me. I have actually provided an example of LaTeX visually on the next slide. And so this is an example of a table. And it has some content about Mick, who's trying to run a marathon, and then there's some different times and speeds and such. And it kind of looks a little funny because it's code. I mean, it's a typesetting language. It's something that you input into the computer in a particular manner that will produce a certain result when you print it. So that's an example of LaTeX. Let's contrast this with MathML. MathML stands for Math Markup Language, and this is a low-level specification for math and scientific content designed to be used on the web. It can encode the presentation of mathematical notation for high-quality visuals. It can also include mathematical content where applications may need to speak what is being visually displayed. And to show you an example of that, on this next slide, we have two columns. One column has MathML code where it has, the angle brackets, it has slashes, it has some different kind of tags, and then on the right-hand column, it actually shows the expression of a sub 1 plus b sub 1. So the computer is given the MathML, and it outputs what you see visually here. So why do we care about these two? Well, they're very different, and this is something that was an aha moment for me as a document remediation specialist. So LaTeX, it's a typesetting language. It's really designed for print. MathML is a computer language designed for the web. LaTeX is meant to be written by humans, whereas MathML is designed to be generated automatically. It's very rare to find somebody who will write out everything in MathML. They're more likely to create an equation visually on the computer and then have that equation be turned into MathML using a certain program that will actually be demonstrated by the next panelist. LaTeX is shorter code. MathML has longer code. Most STEM instructors will be familiar with LaTeX, whereas fewer math instructors I have found have been introduced to MathML. LaTeX is the standard for publishing. MathML is the standard for web. And here's the sticky point. LaTeX doesn't work well, if at all, with your adaptive technologies, whereas MathML will work with the adaptive technologies if all of the factors align. And so the interesting thing about this for me is what our content creators, instructors, are primarily using is appropriate for their industry, but it is very impactful in a negative way for our students with disabilities, as well as for those people who want to have math in a more flexible format. And so you have display services preaching and getting excited about MathML, but the instructors are very much encouraged and expected to use LaTeX. That's kind of an interesting industry discipline perspective that I've gleaned from this. Let me touch on one more thing before I pass off my part to the next panelist. Is I want to talk about what factors have to align in order for MathML to be used, for math to be accessible, and so on. So on this last screen, I have identified 3 different columns. One column describes where STEM is housed, and that's essentially where do your math equations live, where do your scientific expressions live. They could live in physical handouts or in any other physical format. They could live in an electronic document, such as Word docs, PDFs, PowerPoint. They could live online, maybe directly in a website, or in learning tools like MyMathLab. You also find them in the classroom, whiteboards, chalkboards, overheads, smartboards, document cameras. Expressions are being created on the fly by instructors and students that are strictly in a visual format. The second column is talking about how the math content is actually created within those different elements. So, for example, in the electronic document, let's say a Word doc, you could take a screenshot of a math equation. That's an image. You could then paste it into your Word document. Visually, it's there. Accessibly, though, that's not going to be helpful for those that need math in a more flexible format. And so that's where MathML can exist in electronic documents, as well as like a graphical version of the expression. Or you can even have like a text version where maybe it's written out in prose of, you know, A sub 1 plus B sub 1 is written out in the long text as opposed to really using like the symbols or elements and such. And then the third factor we need to incorporate into all of this is the end user's tool. So perhaps they're using a screen reader like JAWS, NVDA, VoiceOver, Chromevox. Maybe they're using a text-to-speech engine such as CAR, which is Central Access Reader, VoiceStream, or the built-in text-to-speech on your Mac. Or perhaps they use speech recognition to dictate math. Maybe I don't have use of my hands, so I rely on technology to type out what I am saying verbally regarding my math expressions. And so it's not a perfect relationship between these three different columns. So for example, MathML is really not supported in PDFs. So PDFs plus MathML, not really an option. And because MathML is not really an option in PDFs, you really can't use, for the most part, a text-to-speech engine with a PDF that contains math. And so this is where your display service folks are expected to know like all of the different sort of nuances of what is accessible in which environment. So what you need to know, if you remember none of these details, is the factors and the stars have to align in order for math to be speakable on a computer by an assistive technology. And it can get complicated. You don't necessarily need to know the intricacies of that complexity, just know that there are many factors that go into making this process accessible. And just for numbers, we'll end on this note. A good rule of thumb is you may think, well, how long does it take to remediate a document that contains STEM? I'm using numbers strictly from the University of Washington. This is what my team has consistently output over a couple of years of experience. STEM is going to take about 10 times as long to be made accessible compared to non-STEM. So for an English book, give it to us, my team will convert it. We will convert about 100 pages per hour. Give us a biology book full of math equations or a statistics book, that number decreases to about 10 pages per hour. So if you are trying to make math accessible, know up front that it will take your display service folks, and it could take you a little bit more time simply because math is really a different language. It's not English. You read it left to right, top to bottom, but not before the parentheses, but not after the factorial, and so on and so forth. So now we are going to hear from our next panelist who's going to tell us a little bit more about how to use a tool called MathType that can produce MathML. So go ahead and take it away, Vicki.
Can you hear me?
Yeah, you're good, Vicki.
Okay, good. Okay, so I'm from Columbia Basin College in the Assistive Technology Center, and we are going to demonstrate MathType, which we've used a lot because we have a student who is blind, and so we are recreating all the math so that we can turn it into Braille. So first of all, MathType is a program that works really well within Microsoft Word, and that's usually where we produce all of our math. We do have to retype it, but we use MathType to put in the math equations. Can't get my next slide to go. There. As you all know, math is a real challenge. The initial books are not accessible, and we have taken our lower math. That's usually what we end up doing, is the below the 100 maths, and we have gone to the extent of retyping the entire book into a Word document because math just is not accessible. And some of the history is that math is just too difficult, which it is. I really dislike this math. It's too difficult for most students with disabilities. Well, math isn't the problem, it's the way it's written, as we all know. Design science, they reject these notions as aggressive and insulting to people with disabilities, which is true. And thank goodness for this program, because our math books are not accessible. So what this is showing here is this is done in math type, this plain text, and then it's turned into Braille. And how we end up doing it is we type it into the Word document and just save it with the math type regular, and then we go to our Brailler. We use Duxbury software with our Juliet Brailler, and it just converts it really nicely. We don't do any conversion in the Word document. We do it when we get to the Brailler.
Hey, Vicki,
Yeah?
I'm just going to interrupt real quick. Can you go into presentation mode so that people can see the slides a little bit better?
I thought I was in presentation mode. Is that now?
No, I think, you know what, I think if you have multiple monitors, you might be sharing one monitor and not the other.
Okay, let's see. Let me just get, oh, shoot.
Get me to, I can take the sharing away from you.
Can you I just lost my window.
Oh no, yeah, here, I'll actually, or you know what, I can, I'll share my PowerPoint that has your slides.
Oh, thank you. I apologize.
No worries. Okay.
Okay, thank you. So you guys can still hear me, right?
Yep.
Okay. So I'm going to go to the next PowerPoint slide. Actually, what I'm going to do is I'm going to try and do a sharing. Okay, so can you guys see me now?
Yep.
Okay. Yep. Okay, so what I'm going to do now is this was from a PowerPoint right here. And what I'm going to do is I'm going to go recreate this, or not a PowerPoint, a PDF. I'm going to recreate this with math type. Now, you can get math type up on the ribbon, but I've made a shortcut in my quick access toolbar. And we use the inline to create the math equation. So I'm going to click on this. Can you see the math type window?
Yep.
So what I'm going to do is you can configure this the way you want. You can select things and put them down on your little toolbar down here. Because we do the simplest math, we don't really need to do a lot of statistics or anything, but there's a lot of options in here for doing math. So what I'm going to do first is, because problem A is a fraction, I'm going to hit the fraction button, and then I'm going to go and, well, I got to turn my math type on, my 18, and then I'm going to tab down 10. And to get this to insert into a Word document, you just hit the X and say yes. Now this is in math type. You can tell the difference because it comes up with this interesting boxes around it. So then I'm going to just do the next problem, and this is, and you'll notice that if there are any variables, they will be italicized just like regular math is written, which is kind of nice. I don't have to worry about it. But that is not what I want here. It's not an X, so I'm going to use this timetables right here. Maybe that is an X, yes. And then you're just going to input it just like any other math equation. And then input it, and there you go. Now, the typical way that math type works is you can't put any spaces. So if I'm going to go like this, you just hear this noise. If you want to put text in, you'll come up here to Style, select Text, and then you can do anything you want in here. So you can make a lot of changes just by doing the text. But I'm just writing without any spaces or anything, and it's inputting it. So now when this gets ready to be taken to the Brailler, these problems, of course, they'll be lined up as problems with the word part, but they actually turn out. When we're at the Brailler, we use the LaTeX, and we choose the kind of Braille that the student uses, which is grade 2, and then it converts it, and then we print it off. So this is a sheet that we've done. You can see here that this whole section right here was done in math type. This one and this one, and of course you can type in words if you want to. You know, you can type in the whole you know, text if you'd like to. I prefer doing the text in Word and then going into math type and putting in the equation, because sometimes when you're typing, let's say you're doing one of these, if you do this, it moves the line across, and then it just gets bigger and bigger, and sometimes you kind of forget where you're at. So I just prefer doing everything in math type that has to do equations, and the words in the Word document. So that is all I have, and hopefully that explains it enough. It's quite easy. If I opened up math type from the ribbon, there's a lot more selections, but since we only use simple equations right now, I just put it up on my toolbar, and it's great access to it. So now I'm going to turn it over to the next presenter.
Awesome. Thank you, Vicki. That was, I think a lot of us rarely think of how it will convert to Braille when we're typing things up, so that was awesome.
I do have that picture, but of course looking at it you can't see the Braille math. If you get good at numbers, then you can touch it and find out where they're at, but so far it's been quite trustworthy.
That sounds amazing. All right, next up we have Nicole Johnson and Brene Hempel. Am I saying that right, Renee?
Yeah, Brene Hempel.
Okay, great. From Central Washington University, and they work at Central Access. You guys provide a lot of document conversion services to ensure that students have accessible material and tactile graphics, so I will let you take it away.
All right, thank you very much. So as she mentioned, I'm Brene Hempel. I'm the Central Access administrator, and I'm Nicole Johnson, the tactile graphic coordinator. And we're kind of just going to do a really quick overview of some methods for tactile graphics and then some overarching just good practices. I'm also including a ton of links, so I definitely suggest checking those out. The slideshow is going to be made available to you guys afterwards. So basically what a tactile graphic is, it's just translating visual information into tactile information so that it can be felt instead of seen. Just a quick overview of the methods. There's a lot of different ways that you can go about making tactily distinct objects and learning content. So just some...
Hey, Nicole?
Yeah?
Could you speak a little bit louder or get closer to the mic?
Oh, yeah.
Thank
what about
you.
now? Is that better?
Yeah, I think that's better.
Okay. Yeah, so these are just a few of the methods. We'll touch on each of them independently. So, yeah, for example, there's some new tech things like 3D printing. Also, a lot of embossers have the option to make pictures with the Braille matrix. Microcapsule paper is also an option. It's swell paper. That's what we use in our office. There's also things like vacuum forming and then just low-tech handicraft methods if you don't have the resources for the other ones. And there's definitely pros and cons to each method. The optimal process is going to be largely situational. If you are interested in a breakdown of the cost or time and quality, there's a good breakdown of that in a table in an article that I'll refer to at the end of the slideshow. All right, and I'm briefly going to talk about the different types of tactile graphic methods, and then I'll turn it back over to Nicole for a little more detail. So 3D printing is something that's new and exciting. We've probably all heard of it, and it's becoming cheaper and more readily available. A lot of campuses already have a 3D printer that you may be able to access. You don't have to buy your own. And this can be really beneficial for topics that don't really work well when they've been converted into a two-dimensional format. So things like geometry shapes, and then we're really excited to use this with geology and geography students since some of those topics are hard to convey in a two-dimensional form. Embossing is another method. If you already have a Braille embosser, a lot of them have the ability to use the Braille dot matrix to create embossed graphics. And so these may not have as much detail as some other items, but these can be really cheaply done and easily done if your embosser can do those. So it's something to research because it varies by machine. Microcapsule paper, Nicole mentioned, is the method that we use in our office. So I'm a little bit biased, but I love this stuff. And it works so there's alcohol in the swell paper. It's a special type of paper. And when you print on the paper with ink that has carbon in it and then expose the paper to heat, it will cause the ink to raise up. And so it's basically, we take the paper and put it through what amounts to an easy bake oven. And whatever textures or drawings around the paper will raise up and then can be felt. And it's so you can create a lot of different topics using this, or cover a lot of different topics. Everything from graphs to maps, and we've even done anatomy and other complex topics with these. So vacuum form is something that holds up really well to time because, like with the microcapsule paper and some of the other methods, as you use those, they kind of deteriorate, some of the texture rubs off. And so vacuum form works by putting an object under the vacuum form machine, and it will create a relief of whatever's under there. So the plastic's heated up, and it will suck all the air out and then mold around whatever is underneath of it. So, creating campus maps can be useful with this way if you have a model of it and other items. And then some low-tack methods can be really good because not everyone has access to, a 3D printer or microcapsule paper. One thing that we give out to all the professors on campus that have blind or low vision students is WikiSticks. And they are basically string that's covered with wax, and so you can, form them and they can retain their shape. And those can be useful for in-class use as well as like if the student comes into your office. Collage methods using different tactilely distinct crafting supplies could be really useful as well. So you can use pipe cleaners and things like that to create shapes and convey information. And then Mylar paper is another method that we use on our campus. And so it kind of reminds me of those old overhead projector sheets. They're clear and it's a little bit thinner. And so when you write on it with a pen, it will raise up. And so when you flip it over, whatever you've drawn on the paper, you can feel like a relief of that. And so those can be really helpful for like math classes and things like that if you're trying to show like this is what a graph is if you're doing something in class. So Renee just went over a few of the different methods, but there's definitely some best practices that extend toward all of them. So you're going to want to be really aware that the tactile senses are a lot different than visual senses. So it's not a matter of tracing an image verbatim. So an example is the image I have on the screen now. You can see that there's a lot of the visual components just totally stripped down. There's three-dimensional depth perception that's not really going to come through in a 2D graphic. Use of textures to indicate that that's a continuous space, etc. Oh, and there is a really, really good comprehensive overview by Lucia Hasty at tactilegraphics.org. She is one of the co-authors of the BANA guidelines, so I definitely suggest checking that out. She has a lot of overview of the methods as well as these best practices. So just a couple things to be aware of. If you're making a set of graphics, one of the most important things is consistency in a set. So for example, if you're doing something one way, you're going to always want to do it that same way. It'll be way more helpful to the user. Kind of similarly, the example that's on the screen right now, you can see there is a key at the top for the line textures. If you're doing things like on graphic keys like that, you're always going to want to have them in like the same exact spot so that the user knows where to find them if they're there. And then I thought this was really interesting about readability. This was taken from the tactilegraphics.org website. Just to be aware of when a user's like reading the graphic, a combination of movement plus texture is tactile perception. There's also an 1/8 of an inch rule, which kind of basically says don't, like our fingers are not able to distinguish things that are smaller than an 1/8 of an inch. So spacing is huge. You're going to want to make things big. And then contrast between elements in the graphic as well. So we kind of do that by having our axis lines always really not distinct at all, and then the actual line on the graph to be bigger, more textured, definitely so the user knows that that's the most important aspect of the graphic. And then, yeah, orientation, keep things consistent. Here's just some more best practice resources. So the BANA guidelines are great, and they're very comprehensive. It's pretty long. It's really dense, but if if you have a question, you can probably find it there. Also, the APH has a good guidelines for design as well. So yeah, I definitely suggest checking these resources out further. So what we've talked about so far is kind of just in mind if you're actually producing the graphic. There's also a lot more resources if you're looking for pre-made graphics. And I'm only going to list about 3 of the libraries. I'm sure there's more out there, but definitely explore these resources. The American Printing House for the Blind has a good library that has just templates with good tactile designs. There's some good 2D and 3D graphics included in that one. Be Tactile is another good one. It's a compilation of 9 different libraries all across the world. There's about 4,000 graphics in there right now. Again, it's just 2D and 3D graphic designs. And then the last one, this one is still actually in development. It's being developed by Benetech and the Diagram Center, basically as a collection of accessible STEM images. And what's cool about this one is that they offer more modalities than just 2D and 3D graphics. So they have like long text descriptions, MathML, things like that. So it's not just a tactile graphic library, rather an accessible image library.
Right, and then some advice from faculty, and as Krista mentioned before, production takes a long time, especially when we're producing tactile graphics, and we need adequate warning. So if it's the day before you need something, we probably can't get it out. So please give us a heads up. It can be helpful, especially with really content-heavy books, to have the professor go through and select the most important images. Because sometimes, especially like we're on a quarter system, and so it's really difficult to get through an entire environmental studies book or geography book in the 10 weeks that we have allotted. And so just picking the most important concepts to be converted into tactile graphics. Additionally, user feedback is very helpful. Please check in with your student, because something that may have worked, last quarter may not work this quarter, and every student's different. So it's really important to know what's useful for them. And then be aware of what resources are realistic for your situation. While it may be awesome to have, the microcapsule paper, if you're on a short timeline, that may not be feasible. Or, 3D graphics, you may not be able to print those at your university or wherever you're at. So just be aware of what you have available to you.
Yeah, so I kind of just wanted to wrap things up with some interesting articles I found that I definitely suggest checking out. The first one is the one that I mentioned that has the breakdown of the different tactile graphic methods, kind of a cost comparison, quality comparison. Yeah, definitely check out these. They're kind of just ways that you work with your students to see like what's working for them, ways to test out graphics. The bottom one is about this cool like magnetic table thing for physics illustrations. I thought that was pretty cool. But yeah, so that's.
Yeah, there's our contact information, so email us if you want to know any more about some of this stuff, because we can only touch on so much of it, and we'll give it back.
And we'll be sending out the webinar materials so that people can access the resources and links provided in the presentation.
Awesome.
Awesome, thank you guys. So now what we're going to do is that we're going to go back to our panelists, and we are going to ask them to just give one piece of advice or best practices that you have for us. So let's start back around with Krista.
Oh, goodness, just one thing. Okay, let me think. I would say understanding how the different adaptive technologies work is going to explain why certain things need to be done a certain way. So it's really important to understand the end user's experience, so you know why like alt text on regular images is important and why math needs to be constructed a certain way. So if you have never seen someone who's blind use a screen reader, or if you've never seen someone who has a learning disability use text-to-speech, or you've never seen somebody perhaps who has cerebral palsy or is perhaps missing their arms never use a text-to-speech, or excuse me, a speech recognition tool, those are really powerful experiences where your mind literally expands to think, wow, if I were to acquire one of these disabilities, I could still do my job. That's what I would say, is really understand the user experience by watching a user use these different technologies.
Great, thank you, Krista. All right, Vicki, one piece of advice or best practice.
Well, this quarter, well, we've done Brailing before. Of course, this MathML can be, or the way that we use MathType can be used with screen readers too. But the thing that is really important is to be in contact with the instructor, get their syllabus. Hopefully their syllabus has all of their test dates and everything, or any supplemental information, because we had to get that done ahead of time, and to pace ourselves as far as time goes. We try to stay ahead of the syllabus so that the student can get their work the same day that the other students do. So it's just a matter of, and like the presenter before, I really love her idea. Use this software. Use all of it, because then you know, when we Braille, you get familiar with certain numbers, and you know, because once it's Brailled, you're lost if you take the sheets apart and you don't number them, unless you're really good at doing, because they put page numbers at the top. But it's also important for, screen readers, so that it reads it correctly. I noticed somebody put a question in there about using the star instead of the times. Well, it depends on what Braille grade you're going to use, but the symbols of plus, minus, times are used with the Nemeth code, and they come out that way so that the end user knows that it is a times table and not an X. So I would say be in close contact with the instructors to stay ahead of the game, because it takes a lot of work.
Okay, great, thank you. And all the way back around to Nicole and Vernay.
All right, kind of echoing what other people have said, I think communication is really, really important, meeting both with the professor as well as the student. As soon as our students sign up for the STEM courses, I'm in contact with the professors, finding out what chapters they're going to cover, and communicating with them on how we're going to convert things and why it's important to get things to us on time. And so early communication is key to being able to produce the materials on time. And also finding out what's working for the student. And I mentioned that can vary by quarter, but different courses, they may have different things that work better for them than in other fields. So.
Great. I know one thing I definitely walked away with was I knew it would take you guys longer to convert our STEM materials, but I didn't realize it would be 10 times longer. So I'm really glad that I'm aware of that now. So thank you all for that. And now I think that we are ready to open it up for questions. Jess?
Yes, we have the questions from the chat, and I just wanted to say thank you to our panelists and moderator for this webinar. Math is not my background, so I'm incredibly grateful for you all to share your expertise in this area, and I really think that point about communication is central here. So I think we have mostly probably faculty and various state workers in the room, and hopefully you're kind of coming away with recognizing the importance of being able to talk to disability support kind of experts to better understand what's possible and how to create material that's going to be converted much easier than trying to kind of fix stuff as you go. So the questions from the chat, and I'll just let whichever panelist wants to jump on to provide the answer, but just to read those out. The first one we have here is, does the equation editor in Microsoft Word use MathML or something else?
Yeah, and I got excited and I answered that in the chat instead of waiting at the end. But basically the answer I provided was the equation editor in Microsoft Word produces OMML, and it's a Microsoft and ECMA created venture. So it's even a separate markup language from what we've been discussing. So OMML is separate and different than MathML. Yeah, I'll just answer that question because that's what was explicitly said. So no, it does not. The equation editor that is built into Microsoft Word produces a different markup language. It produces a markup language that is not MathML. MathML is the ideal.
Great, thanks, Krista. So another question was, as a school, we have purchased MathType for all faculty to download onto their computers. The good news is that we can download MathType on both PCs and Macs. However, when we've tried to download the Math Player on a Mac, we've had some issues. So are there any recommendations for those using Macs when it comes to Math Player?
I'd like to be able to answer that, but we have a Mac in our office so that we can test with Kurzweil and such, but we don't produce our math on a Mac, so I wish I could answer that. We produce it on PCs.
So I'm not completely sure of the answer to this, but Math Player is actually something that's separate and different from anything else we've already discussed. It's essentially a plugin that helps to just speak the math kind of where it's at. And I know, I'm looking at the website right now, it says Math Player continues to support both the visual rendering and math speech in Internet Explorer 6, 7, 8, 9, and 11. It does not work in Internet Explorer 10. So, and it kind of has some bugs in Windows 10. So essentially Math Player is more of a Windows product. So MathType will work on a Mac. Math Player probably will not, based on this quick Google search that I looked up. But I would say contact Design Science, the company that makes Math Player, for a more definitive answer.
Great, thanks, Krista. Yeah, for a lot of things, sometimes you have to just go to the vendor to find out what's going on and troubleshooting that way. So, so there were a couple questions kind of going back to the Microsoft Word equation editor, I think, that's about, does that mean that that other markup language, OMML, if it's not accessible, or does that mean that it doesn't work with screen readers? Can someone kind of speak to the issues there?
Renee or Nicole, do you want to answer before I keep being a microphone hog?
Nah, you can go for it.
Okay, great. So this was my my internal response is OMML is not going to be as great as using MathML. MathML really is the standard for accessible content in the electronic environment. You might be able to get away with using OMML, but it's going to be inconsistent results. It's going to depend upon different versions of maybe your browser, of the technology that you're using to have the math spoken or to interact with that math. It's going to be like if you provided a one-wheeled wheelchair to somebody. They might be able to get some forward motion, but it's not going to be great. So something I will beautifully advertise is part of the solutions that Central Access has come up with is they've come up with this really fantastic tool that helps to do many things. And one of those many things is it will actually convert the OMML into MathML for you. And I believe that's part of their Central Access toolbar, or their CAT toolbar. You could go to their website to get more information about it. I know they've worked hard to keep it free. I'm not sure if that's still the case, but it's a wonderful set of macros. It's an install. It opens up with Microsoft Word. There's a nice ribbon, and then you can run these different macros. One of those macros is taking that OMML and producing MathML.
And just to add on to that, there is actually in the math type in the tab in Word, there is actually a convert editor, and if you click that, it will convert the OMML into math type if you have that on your computer as well. So.
Thank you all. So we had another question about math type. How does math type work through a screen reader, and what about exponents? So this was, I think, something that the group before the webinar kind of talked about how to provide some demos of this, and I'm working to just pull up a quick demo, and we're going to see if I'm going to be able to get the audio going correctly to make this possible. But let me go ahead. I'll share. Hang on. Y'all can bear with me for just a minute while I get all of this going. Oh, goodness. Hang on. See if I can get that screen looking a little bit better for you. Stop sharing one. Back to the other. Okay. All right. So I have an equation document here, which we'll go ahead and open up. And then there's 2 audio clips. And I'll send a link to this page as well when the webinar is over and we send out all of the resources. But what we'll do is I will play these 2 audio clips of this document, and I'm going to zoom in a little bit so that you all can hopefully see it okay. So we have a variety of equations, and what we have here, bear with me, I'm jumping between different computers to make this work. We have 2 audio files, and the first clip that I'm going to play is a screen reader reading the document with the equations created with Word's equation editor. And then the second clip is going to be what it sounds like using Math Player, reading the document where the equations have been converted using math type. So the first example here will be the clip, the kind of inaccessible clip, and then the second one, what happens when you use math type. So hang on. Hope this works.
Matrix example, where, for instance, and, limits and other symbology example. Examples 3.7.2. A dot convergent sequences. B dot absolutely convergent series. C dot sequences with finitely many terms different from 0. A paragraph with a bunch of math in the middle that would make no sense if equations were in.
Okay, so that's Zach put in some alt text that's a little funny there. But what you can tell from that first example is that all of the equations were actually skipped over entirely. The text was read, but that was it. So now let's listen to a screen reader reading the document, having converted those equations using math type.
Matrix example. Kappa to the t power equals open parenthesis, b sub I j, closed parenthesis, where b sub I j equals a sub j I. For instance, open square bracket, matrix row 1, 1, 2, row 2, 3, 4, closed square bracket, to the t power equals open square bracket, matrix row 1, 1, 3, row 2, 2, 4, closed square bracket, and open square bracket, matrix row 1, 1, 2, 3, closed square bracket, to the t power equals open square bracket, matrix row 1, 1, row 2, 2, row 3, 3, closed square bracket. Limits and other symbology example. Examples 3.7.2. Convergent sequences. Cap C equals open curly bracket, open parenthesis, A, closed parenthesis is an element of all real numbers to the infinity power given, the limit as n approaches infinity, of A sub n exists, closed curly bracket. Absolutely convergent series. Script I to the first power, equals open curly bracket, open parenthesis, a, closed parenthesis is an element of all real numbers to the infinity power given, the summation from 1 to infinity, of absolute value of a sub n, and absolute, is less than infinity, closed curly bracket. Sequences with finitely many terms different from 0.
Okay, so hopefully that audio came out okay. And you were able to kind of see a pretty significant difference there with, again, that first version just completely skipping over the equations. And that would have been the document created just using the equation editor from Word. So I think that makes a pretty good case for using math type and kind of demonstrating just what a significant difference that would be for a user having an accessible document or an inaccessible one. So, all right. And sorry, bear with me now. I have to get the questions pulled back up. Okay. All right, and so we had a few more questions. Let's see. One person said, we have not been able to get the equations to be accessible through a screen reader. So does anyone have more information on the accessibility of math type in Word? And basically, this, I think, has to do with kind of which version people are using. And Krista just posted in the chat, so I'll hand it over.
Yeah, so so my response is that UW actually regularly produces MathML Word documents, but we also have more students who have learning disabilities that use text-to-speech as opposed to students who are blind and use screen readers. So if you have MathML in a Word document, it will work nicely with certain text-to-speech engines. Fun fact, if you have a Word document that has been marked up with MathML, and if you use the Central Access Reader, which is a free text-to-speech engine brought to you by our friends from Central, you can actually export that Word document to an HTML format. And MathML and HTML tends to be more popular than MathML in a Word doc, but MathML in a Word document lets you to transform it into different outputs easier. And just kind of as a quick summary that I put in the chat is math type is a tool to create MathML. MathML is the markup language, and math player is a tool used to read the MathML aloud. So lots of math terminology there, and I tried to separate and simplify as much as I could.
Thanks, that's awesome, Krista. Excuse me, that's awesome, Krista. And yeah, I think that might be kind of the issue with that question of if they're using math player or not. And so when you use math type, my understanding is when you use math type to create, an accessible document with math equations, then the user is going to be using math player, which is a free download in order to read math type, correct?
I mean, they could, but technically you could use the Central Access Reader to have the math read out loud. So, and you could also use like Read and Write Gold with a plugin or something. There's a couple of options. So yeah, Math Player is a great free resource. Central Access Reader is also a great free resource.
Great, thank you. And so a few more questions about kind of what platforms these work on. So we had one question from the chat about math type working in PowerPoint. So can you cut from Word and put into PowerPoint in order to use math type? And I think Chris is going to post this in the chat with a link that in recent versions of Microsoft Office that this should work. And so there's the update from the vendor. And there was another question in the chat if MathML can be used in Canvas or if it's better to convert it to HTML and then paste into Canvas pages.
Ooh, Vicki, do you know that answer? Nicole, Renee, do you know that answer?
I don't.
I also don't know. So.
Okay. This is a little bit older, and it's not going to be the best answer. But I know about 2 years ago, in winter of 2016, I was with my colleague, Dan Comden, at the university, and we were testing out Canvas's built-in equation editor and math type and MathML. We were playing around with different combinations to see what was possible. Because that was 2 years ago, I don't want to say one way or the other how it went. I would say for the best answer, contact your campus vendor, or there's a couple of other like listservs that we could check. I do remember when we did some copying and pasting, essentially what it would do is it would take the math equation, keep it as an image, and then it would add text behind it, but it would kind of be in like a math prose format. So it was not the most accessible. So that's a really great question, is the moral of that story.
And I'll also try to follow up with Zach on that, because I think he's spoken about the Canvas equation editor in the past, and I can't quite remember.
Yeah, Zach would know.
Cool. And then I'm going to try and keep with the questions about math type and math player real quick. So there was another question about math player. Will it also read the word text, or is it just for the math? So that second audio clip that I played was using Math Player to read the document. So it read the text as well as the equations. Yeah, I don't think you have to skip between screen readers or text-to-speech in order to get, have one reading the text and one reading the equation, but can just use the one. And then there was also a question about if any of the panelists know anything about LawMap. So I'll pause and see if anyone has anything to say. Otherwise, I might be able to speak a little bit to it. All right. LawMap is a kind of, I think, application developed by a faculty member in the Community and Technical College system, David Lippman, and it's a really great kind of openly licensed resource that I think a number of people use. And I know he's very interested in revising it to ensure that it's fully accessible, but we've had some struggles kind of tracking down where he can kind of get that expertise and consulting. So all I can really say is that I know that the creator of LawMap is really interested in exploring kind of just how accessible it is and how to make it better if it's not fully accessible. But that's all I can say about it right now. So, all right. I think that hit on all of the questions that people had. So thank you again to the panelists and for sharing such valuable information that I think really helps address the STEM fields and really shows that it's kind of a different beast when it comes to accessibility, and that there's some really great resources out there for people. So again, we'll send out all of the webinar materials to those registered once we get the recording processed and sent out for captions. So thanks everyone for attending, and thanks again to Eva and Krista and Vicki and Verne and Nicole. This has been a really great webinar. So.
Yeah,
bye, everyone. Have a good.
Yes.
You're welcome.
Yes. Thanks. Happy Tuesday.
Bye.
Bye.